Hi, so today I'll be talking about the contraction mapping theorem. And the contraction mapping theorem is also known as the Banach fixed point theorem. It is one of the easiest and most useful theorem for constructing solutions of linear and nonlinear equations. And this theorem is named after Stephen Banach, which is born in 1892, who first stated this theorem in 1922. And the following is Stephen Banach. So before looking at the theorem, let us look at the definition of contraction, as we will be using it in our proof. So for contraction, it means that making the length shorter. So we let D in the domain D in Rn, and a function f with domain D to Rm is called a contraction if there exists a number constant C which is greater than equal to 0 and less than 1, such that the distance of Fu and Fv is less than and equal to the constant C and the distance of U minus V. So this is a Lipschitz function with Lipschitz constant less than 1. And the following diagrams has illustrate the definition of contraction, which is making the length shorter. So next, we will use the Cauchy sequence in our proof later, where Cauchy sequence basically means that making the distance a sequence of points, and the point will become closer to each other until their distance is less than epsilon. So now let us look at the contraction mapping theorem, where the theorem states that we let the domain D to be in Rn to be closed, and the function f from D to D is a contraction, which is the definition we stated just now. Then there will exist a unique point U in D such that Fu is equals to U. So basically this theorem is saying that we want to contract and domain, and when we contract it until infinity, we'll get a fixed point where it is the limit, and we want to show that the fixed point is exists, and the point is Fu equals to U. Then we will prove this theorem in two parts, which first one is we need to prove the fixed point exists, and the second part we will prove that the fixed point is unique. So the first one, we will prove the existence of the fixed point, where we will let x to be in D, and we consider the sequence of fkx from k to 1 to infinity. And this sequence basically means that we perform the function f for k times, and k times will be from 1 to infinity. So lastly, we'll perform it infinity times, and so we can contract the domain until it is only one small point, which is the point we are finding. So by the definition of contraction, we will get that fk plus 1 minus fk will be smaller than equals to the constant c power of k, fx minus x. And if we have m to be greater than k, we will get the following: fm minus fk will be smaller than equals to the right side, as this is the dismantle or small parts of the one on the right side, fm minus fk. Then we take out the constant, which is cm minus 1 and plus cm minus 2 plus until ck. This will be larger than equals to the upper one that we have separated, and next, the cm minus 1 plus cm minus 2 until ck, we can write this as a summation of c power of j, and this is a geometric series. And since the number of c is less than 1 and its absolute value is less than 1, we can write it as c power of k over 1 minus c. And this one, since we have the absolute value of c to be less than 1, and for all epsilon greater than 0, we can make the whole thing to be less than epsilon when we choose large enough k. So the whole thing will be very small. And then for all epsilon greater than 0, there will exist a big L, and for all D and M greater than equals to L, we will obtain that the distance of Fm and Fk will be smaller than epsilon, where this one is what we want to prove, which is a Cauchy sequence. Then it has a limit, as we need to prove that it is Cauchy sequence. It has a limit, and we can find a fixed point. Then, since we have the domain D to be closed, we define the limit to be f infinity x. It will be in the domain D as D is closed. And we claim that this f infinity x is the point we are finding, the fixed point of f. Then we want to show that by the definition, fu equals to u. So we substitute the f infinity of x into su, and we will get the following, where f we write it as limit k to infinity fk. And since this function is a contraction, it is a Lipschitz function, and we know that Lipschitz function is continuous. Therefore, we can write the limit outside and we perform the function first. Then we get that f power k plus 1. And we know that this is also f infinity x. So we have successfully proved that f infinity x is equals to f infinity x. Therefore, we have shown that a fixed point must exist, and the point is what we define as the limit f infinity x. So next, we'll prove the second part, which is the fixed point is unique. And we will prove by contradiction. So we assume that there is two fixed points, which is u1 and u2. And we assume that u1 is not equals to u2. Then by definition, we get that fu1 is u1 and fu2 is u2. Then we will get that the distance of fu1 and fu2 is equals to the distance of u1 and u2. However, this is a contradiction, as from the definition of contraction, we need u1 and the distance of u1 and u2 to be greater than the function applied fx minus fy. Yeah, therefore we show that a fixed point must be unique. And now let us look at a simple example of the application of contraction mapping theorem. Here, we want to show that there is a unique fixed point in the domain from -1/2 to 1/2 for the function fx equals to 1/3 sine square x. And we'll show this using the contraction mapping theorem. So by the definition of contraction, we have the fx minus fy is less than or equals to c and x minus y. And by the mean value theorem, we can write this into fx minus fy is equals to the derivative of c and the absolute value of x minus y for some c in the x and y. Then we can find the derivative of x, where it is equal to 1/3 sine 2x. And the absolute value, since we know that the function of sine is between -1 and 1, and we apply the absolute value, therefore the sine function will be between 0 and 1. Then we can obtain that the f prime x absolute value is less than or equal to 1/3. Then hence we have find that the constant c is 1/3, which is less than 1, and this is a contraction as it matches the definition of contraction. So the function fx is equals to 1/3 sine square x is a contraction on the domain -1/2 and 1/2. And by the contraction mapping theorem, we have successfully shown that f has a unique fixed point in the interval. And that's all. And this is some of the reference used in this whole presentation. Thank you.